Okay, let's do an example. This is example 1511 from your text. Okay, here we have a ball B, which is a 2 kilogram ball coming in at 1 meter per second, and it strikes ball A coming in from a different direction, 30, or let's go 3 meters per second. And so we need to define a line of action here where these things hit, line of impact actually. So line of impact, which will go through the centroid of both of these objects. And once we have that, we can draw a perpendicular to that. Let's say this is in the y direction and this is in the x direction. Okay, so this is an oblique impact, so let's use our ideas for oblique impact. And let's start by looking in the x direction at what's going on. Let's call this positive. So our velocity of A in the x direction is going to equal 3 times cosine of 30 degrees. And we can calculate that out to 2.598 meters per second. And our velocity of B in the x direction, our initial velocity here that we have in our schematic up above, is minus, because it's heading in the minus direction, minus 1 times cosine of 45 degrees, and that is minus 0.707 meters per second. Okay, there are no external impulses. We're going to use then conservation of momentum here. So the sum of the masses times the velocity initial equals the sum of the masses times the velocity final, or mass of A times velocity of AX. Again, we're doing this all in the x direction. Initial plus mass B, velocity B, x initial equals the mass A, velocity A, x final, plus the mass B, velocity B, x in the final direction. Again, let's keep this positive in this direction. So we have mass of A is 1 kilogram times the velocity of A is 3, or let's put in what we calculated up above, 2.598 plus 2 kilograms times the velocity of B. Well, velocity V is in a negative direction, 0.707. And then this equals mass of A, velocity of A, x2 plus mass of B, velocity of B, x2. Of course, we can replace these masses with the quantities that we have, and we see that we are missing velocity of AX2 and velocity BX2. Now, one thing I forgot to add here is that our coefficient of restitution, E, equals 0.75. So we need to know this coefficient of restitution to solve for our final velocities, because we have two unknowns in our momentum equation. And so we need a second equation to do this, and we're going to use this restitution equation because we've got velocity b at 2 minus the velocity of a at 2 divided by the velocity of a initial minus the velocity of b initial. So the change in final velocity over the change in the initial velocity. So this is going to equal v of b at 2 minus va at 2 divided by, and we'll just put our initial values in here that we calculated, 2.598 for the velocity, initial velocity of a, minus a negative 0.707 for b. So then we can figure that velocity of b minus velocity of a final equals 2.482. So we can get a relationship for velocity of a, for example, or b, and substitute it into our equation that we solved for our momentum equation, conservation of momentum equation. And that'll give us a velocity of a in the x direction of minus 1.26, and the velocity of b in the x direction equals 1.22 meters per second. So that means that a is heading this way and b is heading this way. So if I'm going to draw these arrows like this, I should actually write maybe a so velocity of ax2 equals 1.26 meters per second in this direction, and the velocity of b of x3 equals 1.22 meters per second in that direction. Now, these are only the x components of the velocity after impact. The y components also will use conservation of energy here. However, in this case, mass, the sum of the masses times the velocity initial equals the sum of the masses times the velocity final. We're going to end up with mass of velocity ay equals mass of velocity ay2. So the initial velocity equals 5. This simplification can be made because if you look at our diagram here, what's occurring, mass times the velocity in the y direction initial doesn't have an impulse component here, and we can of course use this impulse momentum relationship for the individual particle then instead of the system, and we'll end up with mass times the velocity in the y direction initial equals the mass times the velocity of in the y direction final, which means these m's can cancel out, and we just get that the velocity of a initial equals the velocity of a final. So calculating our velocity in the a direction then initial is going to be, again, for a 3 meters per second times sine of 30 degrees this time equals 1.5 meters per second, and the velocity of b in the y direction initial equals minus 1 sine. It'll be minus 1 because B will be down. Minus 1 sine of 45 degrees equals 0.7071. And here's a schematic of B, particle B. And again, the resultant velocity initially is in this direction for B. So our velocity is down initially, and that means our final velocity is down. Notice that our final velocity is in the x direction for B is pointed in this direction. So our velocity of A initial equals our velocity of A final equals 1.5 meters per second heading up. And our velocity of B equals our velocity of B final, and it's going to equal 0.7071 in the down direction. Also in meters per second. So B heads off this way in a velocity of 1.22 in the x direction and velocity of 0.7071 meters per second in the y direction. We can certainly calculate this angle if we wanted to. We call this angle, let's call this theta, which is approximately 30 degrees, and a magnitude of our velocity, B, is going to be equal to the square root of, and this is our velocity of B. So, be heading in this direction. And the velocity of A heads up at 1.5 meters per second and over at 1.26 meters per second, which means the magnitude of the velocity of A is in this direction, and phi equals, with phi equal to 51.34 degrees. Actually, this is closer to just 50 degrees.